Hello, everyone. My name is Tianhao Wang, and I'm here to present our paper called the Locally Differentially Private Protocols for Frequency Estimation. This is a joint work with Professor Jeremiah Blocki, Ninghui and Somesh from Wisconsin Madison. So differential privacy is the standard of collecting user data and protecting user privacy. So in this classical setting, there is one centralized data collector and many users. And the user will send their raw data to the collector, and the collector will add noise and do some perturbation to output the result as a public database or as a database the third party or someone has access to. So then this third party can query something or do some data mining task based on this database or data synopsis of all the aggregated data. Intuitively, differential privacy means that the decision to include or exclude the individual's record has minimum influence on the outcome. And the smaller epsilon here, which we call privacy cost or privacy budget. The smaller the privacy budget, the better the utility, the better the privacy. Note that one issue here in this setting is this centralized collector should be trusted, which may not always be the case, especially in the very sensitive question setting. The notion of local differential privacy hope to overcome this issue by each user add noise locally and then report directly to the database. So note that there will no longer be any worry about the untrusted server. So hopefully with this we can people are more willing to deal to share their sensitive data. And we have seen some working systems. So this one is called RAPPOR, which is proposed by Google, and it is an extension of Google's Chrome browser to collect user browsing behavior statistics. And also Apple, I think maybe some of you have been in the talk this morning. Apple is also starting to collecting and analyzing user health data and spelling data and frequent emoji, something like that. So the notion of differential privacy actually is not new. It actually comes from 1965, which called the Warner model. This is actually a survey technique for private questions. So in this model, for example, the survey people will ask a question, are you a member of the Communist Party? And each person on its perspective will flip a secret coin and then answer truth if the coin comes up head, and otherwise answer randomly. So for example, if the coin is unbiased with so comes up with a probability 0.5, then the communists will answer yes if with the 75% of probability, and no with the 25%. So to get an unbiased estimation of this distribution, if we use these notions, N is the total number of users, N sub V is the number of communists, and I sub V is the yes answer received, we will see expectedly I sub V is 75% times N sub V plus 25% times N minus N sub V. So this C of N sub V is the equation or formula to give us an unbiased estimation of N sub V, because expectation of C of N sub V is actually N sub V. So this is unbiased. Yeah, so this secret coin thing will provide which we call deniability So informally, this means the survey people will not be sure about each user's secret even after seeing the answer. So formally, we see the protocol is epsilon LDP if and only for any two values. The ratio of probability generate the same answer is bounded by e to epsilon. So note that this Warner model only handles binary attributes, so we want to handle the more general setting. And so here we propose an abstract LDP protocol. There is each user in the left and a single data collector or aggregator in the right. So first of all, this user will encode his private value into a value x, and then perturb it into value y. So note that this perturbation function here must satisfy epsilon LDP. Then the user will send this value y to the aggregator, who will collect all the value from each user and then estimate C of V for any value in the domain D. So note that here we focus on frequency admission because it is one of the basic or fundamental problem in LDP. There are several existing protocols. One is the generalized version of the Warner model, which we call direct encoding, and another is one specific version of RAPPOR, which we call basic one-time RAPPOR from their paper. And the third one is a theoretical work from Basili and Smith. We call it binary local hash. So next I will go over all of them and try to optimize them. So first is direct encoding or generalized random response. So in this protocol, each user encodes the value into a bit string. And then the user will, okay, sorry. In this protocol, the user will encode the value as it is. So there is no encoding, or the encoding is direct or straightforward. So we assume the value V is from domain big D equals 1, 2, 3 up to D. The user then tosses a coin with bias P. And if the coin comes up head, the user will report true value, and otherwise the user will randomly report another value. By setting value P and Q to be these values, we can see this equation actually satisfies epsilon LDP. On the other hand, the aggregator first should collect all the reports from each user, and if we use the same notations, we have the same kind of expectation, and similarly, this C of V is given by this formula is an unbiased estimation. So this is direct encoding, and intuitively, higher P implies more accurate. But however, when D is large, meaning that when the domain is large, here the P will be smaller. So that's a disadvantage of this protocol. The second protocol is called Unary encoding, or basic one-time RAPPOR in the RAPPOR system. So in this protocol, each user first encodes the value into a bit string, and then perturb each bit independently. So for example, if big D is 1, 2, 3, 4, V is 3, then X is 0, 0, 1, 0, and each bit is then perturbed independently by setting P and Q. P is the perturbation for each bit. Perturbation probability, Q is the perturbation probability. P is the probability that this bit is preserved or not preserved. So if we set P and Q to be these values, this also satisfies epsilon LDP. The intuition here is that by this unary encoding, each location can be only 0 or 1. Thus, for each location, D is effectively reduced to 2. So there are only 2 possible values. The domain size is 2. So especially when the originally when this D is very large, unary encoding will be better. So yeah, so finally, to estimate the frequency of each value, just do it for each bit. So we know for each bit the frequency of ones in this location. Then we know here this is the count for the value corresponding to this location. Yeah, so the last protocol here we present is called the binary local hash. So know that it's from theoretical work. So the protocol description is more complicated than. So we describe a simpler equivalent. In this protocol, each user first hash the value from the big domain D into one bit, 0 or 1. Or like a compression thing. So, and then the user just perturb this bit by probability. So G here is the number of groups. So since the function the hash range is only 0 or 1, G equals to 2. So by setting P and Q to be these values, this again satisfy epsilon LDP. Then the user will report this bit and the hash function to the centralized data collector. Here is an example. For example, D is 1, 2, 3, 4, and this hash function will hash 1 and 3 into group 0, and hash 2 and 4 into group 1. So if the user has secret V equals to 2, so with the probability P, the user will report group 1. And with group probability Q, the user will report group 0. So suppose now the user with probability P report group 1 is 2 and 4. The user will, the aggregator after receiving this will increment the corresponding locations. And yeah, so similarly by this expectation kind of equation, we also have this unbiased estimation for this local hash protocol. Yeah, so I don't know, maybe some of you are not very familiar with differential privacy, but if you don't, just remember the takeaway of this talk. So the main question in our work is that we want to maximize the utility of different LDP frequency estimation protocols. And to do this, we propose a framework to generalize existing methods and optimize them. And as a result, we come up with two methods. One is called optimize the unary encoding, and another is called optimize the local hash. The importance of this work is that by improving the accuracy of the basic task of frequency estimation, we will have improved the result on more complicated problem. Yeah, so to do this, to optimize different protocols, we first measure the utility of each mechanism by its variance. Since this estimation is unbiased, so variance will be an important metric. We propose a framework called Pure. So intuitively, for each output Y, there will be a set of value V called the support. Intuitively, each output will vote for a set of input, and For example, in this BLH support of y, it's all the values that hashes to y. And define P prime and Q prime to be the values such that after perturbation, the original value will support itself with the probability P and don't support itself with the probability Q prime. So, yeah, so as an example, in random response, P prime equals P and Q prime equals Q. So the main task here is then transform from this minimizing this variance into minimizing this this thing which we calculate, and it is the same as a variance. Note that P prime and Q prime here should satisfy all epsilon LDP. Yeah, so finally, pure here means this holds for all input and output pairs, not means in the centralized setting where delta equals 0. Yeah, so first let's look at how we optimize unary encoding. In the original unary encoding, each bit is perturbed with the probability Q in this value and is preserved with probability P. So intuitively, we want to make P as high as possible. And the key insight here is that we can perturb 0 and 1 differently. Since there are more zeros and there is only a single 1, we can perturb 0 with a higher probability, with a higher P, and perturb 1 with a very low P, which is 1/2. So know that this also satisfies epsilon LDP. And the resulted variance will be smaller, which I will give later. So another is optimize the local hash. In the original protocol, the secret is first compressed into 1 bit and then perturbed. Note that the first step, because of this compression, the information loss is much. But the second step is actually pretty accurate because G here is only equals to 2 and the P is the highest possible value. Yeah, so the key insight here is maybe we can try to balance the two steps by first compressing into more groups. So as a result, we have a G equals e to epsilon plus 1. So the technique here is fairly simple, just partial derivative. So if you are interested, please read our paper for details. So let's look at some analytical result. So here we measure variance of this estimation. Note that here you optimize the unary encoding and optimize local hash has the smallest variance. And this is unary encoding, and binary local hash has higher variance. And this also compares communication cost. By hashing, the communication cost is log of n, which is log of number of users, and direct encoding is a log of all the possible values. And the unary encoding, because of the unary thing, the communication cost is actually order of B. And the direct encoding has high variance because of has variance linear in D. So when D becomes large, the variance is large. So and finally, OUE and OLH has similar smallest variance, but OLH has a smaller communication cost. So to conclude, we survey existing protocols and we propose a pure framework and cast existing methods into this framework. And finally, we optimize unary encoding and the local hash and come up with 2 new protocols. And limitation of this paper is that variance is linear in D, which means to carry out this local differential privacy learning thing, we need a fairly large number of users. So basically, there are at least millions of users. And another limitation is this cannot handle very large domains, for example, learning the frequent URLs. Yeah, and we hope to first handle this large domain thing, and we want to handle the set values where each user has a set of values. Yeah, so we have some experimental result evaluation, and yeah, so I don't have much time. So yeah, so RAPPOR, the system RAPPOR has this epsilon, and we have magnitudes better results. And another thing is on answering multiple questions, and by calculation, we show that partitioning users will have better results. Yeah, and finally, I would like to thank my co-authors, and I would like to take any comments or questions. Thank you.
Let's thank the speaker. Okay, if you have questions, please come up to the mic. I think I'm supposed to ask you to state your name and affiliation, but since this is the privacy session, I'll leave that up to you.
Hi, this is Neela Merman from BC Cancer Agency. So I have just one question from your work. It says local differential privacy. Does it allow different users to set different epsilon? How does your proofs can be projected to that setting?
So in this work, yeah, we can allow different users to have different epsilon, but in this work we did not. But to allow different users to have different epsilon, let me see. Just to have this to have the estimation function to be the same for each for each epsilon value. So yeah, so this estimation function. So here we know that p is fixed after fixing the epsilon. But for different epsilon, p will be different. So for each group of users, if they have the same epsilon, we estimate them. And for another group of users having another epsilon value, we can do it for them. Yeah, and finally we can aggregate somehow. Yeah.
Thank you.
I have a question. So near the end, you said G to be equal to, I think, e to the epsilon plus 1,
yes.
Was it? So e to the epsilon, of course, is unlikely to be an integer,
yeah.
but G is. And
yeah.
Like, what is your scale of epsilon? Because ideally, epsilon is like e to the epsilon will be between 1 and 2, maybe, and then G will be between 2 and 3. And what does that mean for a number of groups?
Yeah, so actually in the Google setting, so they use a fairly large epsilon value. In that setting, e to epsilon can be like 81 or some big number. Okay. So in that setting, G, it makes sense to, and just if it's not an integer, just round it or.
Okay, so you're not getting that great privacy then, when e to the epsilon is like 80. That's pretty large. Okay, any other questions? Okay, let's thank the speaker again.
Thank you.